Okay.
So I guess it's 9:03. Okay. So I think we're gonna get started. Okay. Well, so it's a pleasure to have Aratz Beranoguirre with us today. And you may be wondering why he has such a weird name. Well, it makes two of us. Aratz is Basque. So Basque that he's actually more or less from the same hometown as I am. I've known Aratz for many years. He is one of my best friend's little brother's best friend. So, so we go back a while, but we moved away from the Basque Country. Life went on, and we kept running into each other in really weird places, like the middle of Madrid, a city of 3 million people. Why wouldn't you run into each other? A plane going from Germany to the Basque Country. Why wouldn't you run into each other, right? And we were, talking about what have you been up to, and he told me, oh, I'm working geochronology and I'm doing uranium-lead dating of calcite. I said, what do you mean? That's exactly what we're working on as well. And that's where our lives converged again. Aratz is currently at the Karlsruhe Institute of Technology, KIT, in Germany. He is the head of the lab, and they specialize in dating things that are undatable in most other labs because they have too low uranium concentration. So I think this is a topic that can be of interest to many people at the Bureau because Aratz and his team, they can date ubiquitous carbonate. So I think I hope that you find his topic of interest. Just quickly, that's his undergrad at the University of the Basque Country. Then he went on to Granada to get his master's, went back to the Basque Country to do his PhD, and then he worked for the Geological Survey of Spain in Madrid from 2015 to 19. This is when I ran into him in the middle of the city. And then he went on to Frankfurt, and he was a postdoc for 3 years working on the in the geochronology lab over there, which also specializes in low uranium concentration dating. And now he is at KIT, and we've been collaborating with him for a little while now, and we hope to continue our collaboration for many years. So the floor is yours, Aratz.
Okay. Sure. That's you see the screen, right?
In a second, there. Now we get
Okay,
it.
super. So I guess I need to wait like a couple of seconds until when I change the slide. I mean, but well, okay, I will manage to. No, okay. So good morning, everyone. Good afternoon for me. It's already 4 p.m. here. First of all, of course, I'm glad to be here. I'm really so I have to thank to Priyanka, to Jennifer, and to Esti. As Esti told, we are from the neighboring town, and actually she didn't tell, but we studied in the same school, in the same primary school. But Esti is a little bit older than me. But just a coincidence, right? That we get this career in geology afterwards, and we met outside from the Basque Country. So today I will show you a little bit what I've been playing with in the last 3-4 years, which is the uranium-lead chronology of low uranium minerals. You will have a. And so first of all, a little bit of a brief history of geochronology. At the end, it's something that is relatively new because just 100 years ago, 1 century ago, we didn't have much idea about how old the Earth was. The people was thinking more in a religious way than a scientific way. But we were lucky, not we the geologists. I mean, lucky, I would say, as a human being, that there were some clever guys around. That those they are well known already. Henry Becquerel, Ernest Rutherford, or Pierre and Marie Curie. That they discovered the radioactivity. They saw that the uranium and thorium, they had some decay, and actually soon after they were able to isolate the radiogenic lead. Then soon at the beginning of the 20th century, the first papers with uranium-lead dating appeared. This is Bertrand Wolwood and other people. And it started more or less developing this field of geosciences. It was developing the instrumentation, and well, in the mid-century, it's when the physicists start also playing in the same game. And already in the 56 with Patterson, we have some H's that they are more or less close to what we know already. And actually in the 50s is when the isotope traces came out, which is more or less when the uranium-lead geochronology, as we know nowadays, started. Then in the 60s is when the first isotopic dilution Timms analysis came out. In the 80s, the SRIMP appeared, or the SIMS SRIMP. And in the mid-90s, like just 25 years ago, almost 30, the laser ablation inductively coupled plasma mass spectrometry came out. So the first H's, and that's the technique I use. So that's what I will talk about, the laser ablation stuff. So why are we interested in uranium-lead? There are mainly two reasons. The first one is that those two elements are highly fractionated in different minerals during their formation. Uranium is an actinide, which is usually in a +4 state, while the lead is a chalcophile element, and it's generally in +2 valence. That makes them to tend to be in a different mineral. So some minerals are more prone to take up the uranium, while others are more enriched in lead. And together with that, it's interesting to know that the uranium has two different isotopes, 238 and 235, which both are decaying in two different lead isotopes, the 206 and the 207. Apart from that, it's also interesting to know that the uranium lead has different closure temperatures in different minerals, and so that gives us the chance to reconstruct some geological histories, and if we are lucky enough to have those minerals in the same rock or in the same area at least. So as I told you, due to this highly fractionation behavior between uranium and lead, makes that some minerals were highly enriched in lead, some in lead and some others in uranium. The most traditional one, or the most known one, is the zircon, monazite, and to lesser extent, titanate and rutile also. So if I move the mouse, you see, right? My mouse.
Yes.
Okay, perfect. So usually the geochronology has focused on this domain of this graph, where we have high uranium minerals, and we have high this mu, which is the uranium lead ratio. So those minerals have a lot of uranium and almost no lead. But nowadays, due to the advances in the instrumentation, we are able to go to this low mu field. Carbonates are well developed, but also metamorphic garnet and also skarn garnets. But skarn garnets are more like something in between here. They are not that poor in uranium. So this Concordia diagram, I'm pretty sure that the majority of you have seen it, maybe at least in the bachelor. I'm sure that you saw it in the bachelor. Maybe some of you, depending on your topic, you already forgot. But well, this is the Concordia diagram that it was published in the 50s. And here, when we analyze a zircon in that case that has no uranium, both ratios the 735 and the 638 will plot in this what's called the Concordia line. Also, always taking in mind that in the cases where there's no any disturbance in the system, so the system was closed. However, of course, the nature is not ideal. So what happens when a mineral is forming and apart from uranium take different proportions of lead? But for that, there was also intelligent guys around. In that case, we were Terra and Wasserburg, that they create this other graph where we have in the x-axis we have the reverse. So in that case, it's not lead uranium but uranium lead, and in the y-axis we have the lead ratio. And here in that type of graph, if we have domains or minerals in the same rock with a different amount of common lead or initial lead, those analyses will plot in a regression line, and the lower intercept will give us the age. In the next slide, you will see it easier how it works. So imagine a mineral or a sample, a domain, where the uranium-lead ratio is heterogeneous. So at the time 0, the lead-lead ratio will be equal in all the analyzed points. So but as the times goes ahead, the areas with a higher uranium content will produce more radiogenic 206 lead, and the ratio, the lead-lead ratio, will start dropping like that. And that's how this Terra Wasserburg work, and that's actually the one we use for the low uranium minerals. Okay, so how do we measure the uranium lead, or how do we date? They are mainly in our field. There are mainly three types of instruments. I don't want to go in detail here because otherwise I will need a lot of time. But well, we have the TIMS, the thermal ionization mass spectrometer, the SIMS, the secondary ions, and the laser ablation. They all have advantages and disadvantages. The TIMS is by far the most precise method in case you need to distinguish two events that they are very close on time. For example, we cannot sometimes, depending on the age, we cannot do that with a laser. We cannot distinguish the events. But the TIMS, for example, it requires a very long-lasting sample preparation. And well, I don't want to go in detail, but the important fact for us is that for the laser ablation, we need reference materials for doing several corrections that we will see soon in a couple of slides. So the laser ablation, that's a pretty basic sketch of the laser ablation. So we have the laser cell where we put our samples. The samples are regular thin sections, slab, rock pieces, mounts. But there's nothing special in the preparation. It's pretty with a regular material. That's a picture of our laser in Karlsruhe. So we ablate the sample. I will talk, of course, depending on the material, depending on the uranium content, the spot size can be smaller, bigger. We can ablate with higher energy, lower energy. But I don't want to go. That's very technical stuff. So we ablate the sample, we vaporize the sample, so we convert the solid material, the zircon, the calcite, whatever. We convert it in gas, in vapor, and we bring it with argon, helium, and nitrogen. We bring it to the plasma torch. The plasma torch is at 10,000 Kelvin, so more or less all the sample, all the elements are ionized. And through a mass filter, we bring into the detector only the masses we are interested. So in our case, only uranium, thorium, and lead reach the detectors. The rest are missed in the way. And depending on the mass filter, we have 3 types of mass spectrometer: the quadrupole, the sector field single collector, and the sector field multi-collector. They have different well, advantages and disadvantages, but the most important difference is the sensitivity. This ICAP-Q, those are from the brand Thermo. The ICAP-Q is the quadrupole, the element is the single collector, and the Neptune is the multi-collector. You can see it in the graph how the differences in the sensitivity can be amazing. So I told you, sorry. As I told you, for laser work, we need reference materials because we have to do several corrections. First of all, we have to correct for the element fractionation. When we do the laser spot, there are some physical or chemical processes occurring. This is actually not very well known. There are several labs working on that. The people that they are mainly chemists or physicists. It's not well known, but well, to say it in a basic way, it's like at the end the 238 uranium is heavier than the lead. So as we go deep in the hole in the ablation pit, it's more difficult to the 2038 to get out from the hole. So that's why we are creating the element fractionation, and that must be corrected on one side. Of course, it's not that easy, but it was just a very basic explanation. And then we have also the instrumental mass bias. So how do we correct it? For that, usually we use materials that they are very well known, very well characterized. And one of them is the NIST glasses. The NIST glasses are synthetic glasses. For example, the 612, it's around 40 ppms of all the periodic table. So all the elements have 40 ppms. And with those glasses, we correct for the lead, and also for the drift correction. That this is important because during the whole sequence can last like 10-12 hours, and due to the differences in temperature in the room, due to some instabilities in the gases, this drift can be, or the measurement can vary over the time. So this is those blue dots are the measure ratios for the NIST 612. While after the correction, we got to those diamonds that you can see it pretty well. It's around only 1% of deviation or standard deviation. And that's another case. For example, this is the 614. But when we are analyzing carbonates or garnets or wherever, we have to also use a matrix match standard, because the glasses and the rest of the silicates, or even not silicate, the carbonate, they have different behavior against the ablation. And that must be also corrected, which is actually the mass bias that we have seen, here. This initial value to the real value ratio or deviation is different for each of the materials we ablate. And actually, it depends also, the day by day is different. It's not always the same for each material. And this is an example of a Garnet where we have this 140 million years age. After correcting the drift and the lead, the 207-206 ratio, but to that analysis or to that age, we need to now correct the matrix effect, which is called the matrix bias. And in this case, after doing that, we got an age which is 6-7% older, which of course, as the older you go, this difference makes it becomes bigger and bigger. So, and now I will like to show you some some examples of works that we have done in the last year. So I've done, or some of the people in the literature have published. So the carbonates are by far the most developed mineral, the dating of carbonates. But it's only like 10 years ago. The technique started 10 years ago. Those are the first two PhD theses that were done in London, in the University College and the Royal Holloway. And actually, this Queen Lee published the first paper. It was 2014, so it's just 8 years ago, and it was they dated some ammonite cement. And this is the carbonate is also developed in terms of reference materials. There's a lot of people, a lot of labs working in uranium-lead, in the carbonate. So that makes also that the availability of the reference materials is large. This is a picture of our mount, the mount I use, where I have 1, 2, 3, 4 different materials, and I also have this B6, which actually I love. This B6 I find the best one. And I know that there are a couple of groups working in more to publish more reference material. So hopefully in a couple of years there will be more in the business. And now we have some examples that what I told you, Esti, before, that probably you are familiar with this type of rock. This is because in the Basque Country, where STA and I am from, this it's a limestone, a red limestone it's red due to some anoxic conditions, and it's full of rutile. It's very popular for like as a building stone. So there's plenty of town halls and banks and like official institutions that they have this type of rock. So when I went in Christmas to my parents, I went to the quarry where those samples are coming from. I took a couple of samples and bring them with me, and I was able to analyze them a couple of weeks ago, and that's what I got. I was surprised that I was expecting this age because the stratigraphy is known and we know that it's like Aptian, Albian, the Cretaceous. But I was surprised, because look at the uncertainty. It's just 1 million years. It's a 1.5%. That's crazy. I mean, I was not expecting, so I was really surprised. And now I would like to contact, because I come mainly from the metamorphic world, so I'm not very knowledgeable about fossils and sedimentary stuff, but I'm excited. So I hope to collaborate with some colleagues here about, I don't know, what we can do, if we can do some stable isotopes or paleoclimate analysis to see how was the ocean at that time in this Basque Country in what was going to be the Basque Country afterwards. And yeah, that's pretty new. So, and I interpret, of course, that this is the sedimentation age or the maybe early diagenesis can be, if the diagenesis occurred just after the sedimentation, maybe we cannot distinguish. Then another type of example, it's those rutile deformation dating, which is pretty popular. There's a lot of work done on that. And this serves you to date several veins. This is a paper of the group from Barcelona, where I was also involved, about the oil migration and the compression related with this migration. Those pictures are from the Pyrenees in several faults and thrusts, and it's interesting. We date a lot of veins. We got different ages, and well, the interpretation, it's not always that straightforward. And this Reuben Hassmann was maybe one of the first papers. It was a geology, was quite impact in the structural geology field. They dated a lot of samples, and then they assess those samples to different tectonic events or thrusts and veins. And actually, I should have put another image for this Hasmanetal paper. Well, it's not in the paper, but the point is, I was sharing the office with the guy that did the analysis, and it's nice because even in a thin section scale, they were able to see three different vein system with three different orientations, and they have three different ages just in a thin section scale. I mean, in 2-3 centimeters, they have three different ages in three different veins. That's amazing. That's another example that can work. Also, the carbonate dating can work for ore forming processes. Those guys, to be honest, they were pretty lucky because in a high temperature, the uranium tends to escape from the crystal lattice of the calcite, so it's not easy to find uranium in those calcites. Actually, I've been working with Matthias, with the first author, and I've tried to date some other mineralizations related calcites, and we got no luck at all. There was nothing to do with them, no rain in the system. That's another example that was also quite an impact in the community. This paper of Xavier Manguenot, that's this was done in the Paris Basin. They recognize different calcite generations. They came to Frankfurt. They date them in Frankfurt, and they find different ages. And afterwards, they combine that with a clumped isotopes analysis. So they were able to more or less depict an evolution of the basin from the burial to the uplift. No, from this seawater temperature, the burial and the uplift. And actually, it's also like 2,003 years ago, and has quite a lot of citations actually. And of course, there's several other applications related with the carbonates. We have the diagenesis. I already showed you this example from the Basque Country. The speleothems actually work really, really well. I don't know why. I mean, the speleothems usually have quite a lot of uranium. Well, quite a lot. I mean, quite a lot. I'm talking about maybe, I don't know, 3-4 ppms. But the point is, they have almost no lead. So those meteoric waters, they seemingly they don't take water, or they don't take lead, or the lead remains in the water while the uranium goes in the speleothems. I have no idea, but they work pretty well. Then we have also the basmasite, the rare earth carbonates. They are a bit tricky. They are not very easy to work with, and well, some methanogenesis or paleohydrology stuff also. And another side study or side effect of those carbonate reference material is this study that I published last year, where we test if the sulfates, we have no reference materials for sulfates, but as both sulfates and carbonates have this calcium as the main cation, we did a test to check if it was possible to use the carbonates as reference materials for the sulfates. For doing so, we took some samples from the Messinian salinity crisis. The Messinian salinity crisis occurred when the connection between the Atlantic and the Mediterranean Sea was closed here between the African and Iberian Peninsula. So the Mediterranean Sea was converted in a lake, and afterwards was evaporated, and they formed some massive evaporitic sequences. And those evaporites have been intensively studied, so they know the cyclostratigraphic age is really, really well defined. And we find that more or less we are getting the same age. It's within error. We cannot improve those uncertainties. It's the maximum we have. It's around or the best we have, it's around 6%. And the cyclostratigraphic ages are within this 6%. And another ongoing project that I find it interesting because that's in the Stuttgart Basin, South Germany, where we have several evaporites intercalated in the mudstones, and we have several hydration and dehydration reactions. And this example, for example, it's very interesting because we have the last fluid infiltration that hydrates the formed anhydrite occurs at 72 million years, like a late Cretaceous. But the areas that they are not rehydrated, they are not affected by the water, they still keep the old age, which at the same time, this old age was also a dehydration reaction, because the anhydrite is always formed after the dehydration of the, well, not always, but that's the most common case, that it's after the dehydration of the primary gypsum. And now let's go with the Garnet. That's a topic that I like more. I like the most because, as I told you before, I come from the metamorphic world, so I feel more comfortable with the Garnets because I understand them better than the carbonates. Here we should, first of all, distinguish between skarn garnets and metamorphic garnets. The skarn garnets usually are more enriched in uranium. They can have up to 70 ppms, and their study is rapidly increasing. Nowadays, it's there are around 10, 20 papers per year. Of all, the Chinese are publishing a lot on this topic, while the metamorphic garnets are more challenging because they barely have uranium. Another problem in the related with the garnet is the lack of well-characterized standards. We have this Mali and Lake Yaco that was published by Seman et al. And one of the co-authors is Stockley, that you have him in Texas, as far as I know, but in the university, not in the bureau. And last year, this Defeng Li, that this Chinese group, they published another potential standard, potential reference material, this PL57, that is nice, work well, but in my opinion, it has well, not in my opinion, it has too high uranium. So for some applications, doesn't work. I mean, it doesn't work due to because we saturate the detectors. It's not any other problem. I mean, the Garnet works pretty well, actually. And we are working in some Garnet that we are trying to characterize them that maybe in the near future can be used. Can we publish them as a standard? So a couple of examples of the skarn garnets in Erzgebirge in East Germany. That was a very important mining area in the past. And well, that's we date several garnets and we find that there were at least four hydrothermal, four garnet forming processes. That it's interesting for the geological interpretation of the area, no? And that's another example from Nico Meyer. It's a PhD student in Tübingen now, in the South Germany. That's also from Erzgebirge. And well, actually, the paper is not in prep anymore because it's submitted already. He has submitted this morning, some hours ago. And in that case, this Nico is working in tin mineralizations. So he finds two different stages of garnet formation. The first one has no tin at all, but in the second one it's crazy because it's all the tin mineralizations came with the second stage, which is like 10, 15 million years later, and the garnet have a lot of tin, up to 7% of tin. That's crazy. And the last, we have the metamorphic garnets. The metamorphic garnets, so far there are only 3 papers published. one in Frankfurt, where I was working with those guys, with Leo Milonik and Axel Gerdes. And there are another two are in Brazil, but Axel Gerdes is also involved. So it's not, it's quite particular, or not just a few labs working on that. And that paper of Leo was the very first one on metamorphic garnets. He dated the straight schist in the USA. And those schists are already known in terms of age due to zircon and monazite analysis. But he demonstrated the garnets can be dated, the metamorphic garnets can be dated, even if in that case, they have only around 70 ppbs of uranium. One of the main criticism that Leo got from the reviewers, for example, was how to deal with the inclusions, because usually metamorphic garnets, and above all those low grade metamorphism stuff, it's usually really low, they have really a lot of inclusions. So he showed he discussed about it, and for example, in the top right, we have time resolve analysis, and we can see how we can consider the first part it's affected by zircon, because we have a high signal of uranium, and this part of the analysis is rejected, while the second part of the analysis, we assume that this is really garnet, because it's more flat profile, more stable, and that's the part of the analysis we consider to afterwards put it in the TeraVas book. Nowadays, we have a couple of, we have several projects ongoing. This is an interesting, some interesting samples from my colleague, from Chao. Those are some xenoliths from the Cabal Craton in South Africa. And we have around 3 billion years or 3,000 million years. But the interesting point here is that the majority of the spots are below 2 ppbs. And here we can even go a little bit farther and go below 1 ppb. That's a sample from northwest Spain, where I did my PhD. And it's a vein cross-cutting everything that only has garnet and quartz. So up to now we were not able to date that. And looks like, now we are thinking about what's the implications, the tectonic implications for those H's that are appearing. And just okay, that one, yeah. I thought we were in the last slide, but no. Okay, this is just to show the improvement in the analytical techniques. No, this is how that's a zircon. That the GJ1 is one of the most used zircons in geochronology. So when we analyze with a laser, with a regular, usually we use a spot size of 20 micrometers, and we go around 10-15 microns depth. That means that we are bringing around 3.5 picograms uranium to the spectrometer. While in the garnet, in those really poor uranium garnets, even we have 200 microns spots, we are bringing only 1 femtogram of uranium to the mass spectrometer, which is around 3,000 times less uranium than in a regular zircon analysis. And now, yes, the last slides. That's just to show you what other labs are working. All those papers, the majority, well, not all, but the majority are published in the last 2-3 years. It's how this low uranium dating low uranium minerals, it's becoming wider and wider world. And you can have nowadays staurolite, epidote, vesuvianite, ilmenite, wolframite, and also scheelites. And that's, I would like to take advantage of the talk to ask for your help in case anyone is working with scheelites, because this paper came out last year. I wrote to this Yang Wen-Tan, to the first author. So he sent me the the scheelite. That's the first paper ever about the scheelite dating in situ. And the points I got, he was very kind. He sent me the standard, but I'm not getting the results he got in the paper. So I'm a bit curious on going further in this topic and see why I'm not getting the same results. So if any of you have any scheelite that would like to share with me that is more or less suspecting DH or no DH, I will be glad to collaborate. And well, that was all on my side. Thanks for your attention. And if you have any question, I will, of course, try to answer if I know the answer at least.
Thank you so much, Aratz. That was great. So let me check the chat. I have a bunch of questions, but let me see. So Stephanie says, for low uranium calcite, what are the range of dates that can reliably be obtained? Are there age limits?
No, in theory. No, in theory, but the problem is for the very, very young, you have the problem that you need to correct for the thorium disequilibrium. And for very, very young, I mean, that also depends what's your range of ages. But with very, very young, I mean below 3 million years. They can be dated. I mean, I have ages of 0.5 million years, 500,000. But they have some corrections. It's a bit tricky. The main issue with the young stuff is that maybe I can share again the screen to show the main issue for the young stuff is here. It's that we need the ratios of thousands. We need ratios, so it's samples that they really have uranium and they have no lead at all. Because imagine that a very young age, there's no almost difference in the y-axis. So you really need a strong spread on the y in the x-axis to have a defined line. But it can be done. Actually, that's why I know the speleotems work super well, because the speleotems have no lead at all, and the ratios are amazingly high. We are talking about 5, 6, 7, 10,000 of uranium lead. And for sure they can be dated. And the oldest, there is some paper some months ago came out that it was like it was already like 3 billion or 4 billion, something those in Australia in the cratons. So they are. It's more or less almost all the Earth time.
Sorry, I skipped one. So we have a question from Julia Gale, and she's asking, what is the upper temperature limit for enough uranium in carbonates?
No idea. That's, I guess it's that's a no. I have no idea. I cannot answer that question. I mean, I've done, for example, in the example of Xavier Manguenot, they go to, I don't know, to 200 or something like that. Above 200, it's a bit more tricky. Yeah, but here I'm not sure if they don't say the temperature. Okay, here it's 90. Yeah, sorry, they say 90, but I guess around 100, 150, 200. It's difficult. Probably these ore forming processes are also high temperature, but I guess this also it's a bit of matter of luck. Well, probably it has a reason behind, but I have no idea.
Okay, thanks.
So I have a question before we go any further. I think that Aratz has been very humble because he has not mentioned that what he can do in his lab and what he was able to do in Frankfurt when he was there as a postdoc to date these uranium or low uranium concentration phases is not common at all. Like most geochronology labs in the world cannot date these things. And we do have a state-of-the-art lab here in Texas. This is Stockley's here at UT. And I have been working with him in his lab. And there are some things that I have not been able to date that Aratz has been able to date. And the problem is being that they have too low uranium for dating over here. So my question is, Aratz, what's special about your system? Like, why are you able to date things with low uranium that other people with regular setups are not able to do?
Well, that's a bit difficult question to answer. I mean, I think it's maybe have a patience to work with the, find the right tuning with the gases, and because I mean the main success, or the main part of the success, comes from the instrument. It's not my something that I'm doing. It's just
but do you have any amplifiers? Like, do you have anything in the system that you use to amplify the signal?
No.
Okay.
It's nothing at all. It's just a good tuning. I mean, for example, for those 1 ppb or below 1 ppb Garnet, I'm using the Neptune, which is a multi-collector in Frankfurt. I'm not doing. I don't have this in Karlsruhe, but in Karlsruhe, Frankfurt, it's 1 hour by train. So I mean, it's not when I can go to Frankfurt and analyze. It's not a big issue. I keep the contact and actually the main problem here it's the background of the gases, because the gas brings a little bit. I mean, the analyte that is in less proportion is the 207. So the 207 is the limiting factor for any analysis. And for example, I guess it was in the helium. In the helium, you have a little bit of lead. So depends a little bit on the company that brings the helium. And actually, sometimes we cannot measure, and it's not our fault. It's just the helium fault, because the helium has high lead, so this lead is affecting to our detection limit. So it's not even us. I mean, the point is we have plenty of people that wants to analyze garnets, and we have some garnets that they are rich in uranium. So we don't care. We are way higher than the background, so we are not in those limits. So when we have a bad gas health or bad background, we do other stuff. And when we have low, we do those really low uranium stuff. Okay. And of course, it's also the age. I mean, when I go to the 3 billion stuff, when I go here, the uranium-lead ratio, it's only 1.5. So that means, that means if I have 1,000 counts of 207, I will have 5,000 counts of 206, and I only need like less than 10,000 counts of uranium. If I go to younger stuff, it's possible. I cannot go that low uranium, because if I'm dating something that it's 10 million years, the uranium-lead ratio is, I don't know, 60 or 70 or 100. So that means that at least I need something that has I don't know, half a ppm of uranium.
Okay. All right. So we have the chat it's filling up. So I'm gonna move on. So Tori Larson asks, the ages on the anhydride and gypsum in one sample were 114 million years and 82 million years respectively. How do you resolve those differences?
But I don't understand. I mean, it's they are not within error. I mean, they are quite far away from each other. I mean, it's 50, 60 million years of difference.
Tori, if you're in the audience, can you please clarify?
Yeah, hey, thank you. That was a really nice talk. I was just wondering, is that I mean, is there a transition from gypsum to anhydride in that sample, or do you think they're I mean, what's
No,
the,
no, I think
what
it's,
are those,
I think
I guess, what do those ages represent?
that's a good question, actually. No, it's because we have, I showed this because this, for me, the image is nice, but we have dated a lot of samples without any knowledge, let's say. So it was like a, okay, here we have gypsum, here we have anhydrite, and it was more or less blind analysis. And then we find that probably they are, we find actually 5 H's, five peaks, that they are probably associated with that some tectonic movements. So they have some geological explanation for those H's. And the point is that this fluid infiltration, it's not homogeneous, because you have some levels that you have the water coming at 120, while other levels like this one, it's losing the water at 120. But the late Cretaceous event at around 70, 80, it's only gypsum. So I guess that was like a massive water income. But it was not, it was more or less heterogeneously distributed. So it was not complete. This rehydration was not completed.
Thank you.
Thank you. All right, so Drew Levi says, hi, Aratz, nice talk. Can you talk a little bit about how you refine/modify your laser and mass spec settings depending on which low uranium phase you're targeting?
There's no difference in the laser or mass spec.
Is the standard?
The technique is the same. I mean, we have to, it's each day, even if it's in the same mineral, each day we need to refine because those are, to be honest, I have no idea. I mean, it depends on the gas health, on the temperature of the room. There are several parameters, and even from one day to the other, even if you don't open the holder, I mean, you have the samples from one day to the other, and there can be sometimes like a 10-20% of difference in the signal, in the sensitivity. But maybe from one day to the other, that much not. But if you take 1 month, you can have without them doing anything. So this is, to be honest, I have no idea. That's coming from the gases or the plasma that maybe it has a different temperature or.
Okay, and so the follow-up question is, and what mass spec do you use at your lab, and what are its detection limits?
Yeah, well, we are using in Karlsruhe, we have the element. We have so but there's no pictures. So I have the element which is in the first slide. This is our lab. This is the laser I have in Karlsruhe, and on the right side is the element. That's the mass spec I have. And in Frankfurt we have the Neptune, which is the same company, but it's the multi-collector. The detection limits, yeah, well, depends a little bit on the tuning, but it's what coming back to the what I was explaining to you. For example, the 207, which is the limiting factor, no, because at the end it's the 207 will limit how low can I go in the uranium. We have around, well, I did it, I forgot, but it's around maybe 100 ppts or something like that for the lead. Of course, the point is the uranium need also to always to be higher, because otherwise you don't have these ratios. But imagine that I tried to have a background when we are lucky with the helium. The background was it's usually around 25 counts only of lead in the background. So I try to have the signal or the samples at least to have 100 ppm, 100 counts per second on the 207, and that could be, yeah, it's probably less than 100 ppts. But for uranium, it's like 800 ppts or something like that.
And I have one last question. I think we're almost up with time. So we find in some cases the host rock has a ton of uranium, but then veins that cut that host rock have very, very low uranium concentrations, to the point that we've been able to get beautiful H's from the host rock, but no H's from the veins. So my question is, and I guess the answer is that it's because uranium is not very mobile. So you're not leaching any uranium out of the matrix. So where is that uranium coming from?
I would think in a different way. The point is why the vein, the country rock is not giving anything to the vein. The vein brings,
right. That's what I mean. Like you're not taking any uranium. You're not, even if you have like the host rock or the country rock in contact with that fluid, you're not taking anything from it, at least not the uranium, right? But I always thought about uranium as being mobile, but I guess it's not.
But probably that's the point, is that the fluid is coming through samples that they have no uranium. Because there was one guy coming in our lab with samples from the Pyrenees and from the Andes, and say more or less the tectonic sketch or the meaning, the tectonic meaning it's more or less the same in both. We're saying some faults and some thrusts and so on. The samples from the Pyrenees almost work all, but you have to think that all those faults in the Pyrenees are mainly in sedimentary rocks, while in the Andes you have way more igneous metamorphic rocks, and the samples from the Andes barely worked. And I would say that, I mean, I'm sure that there is more uranium in the Andes, in the country rocks in the Andes than in the Pyrenees.
Right.
But yeah, I mean, probably it's what you say, it's not leaching to the fluid, while in the carbonates it's easier to move into the fluid.
Okay.
Or something like that. I don't know, but probably must be some explanation on that direction.
Okay. Well, let me see. I think we have answered all the questions in the chat. Okay. Well, let's thank Aratz. I just call you Aratz. Thank you so much. And we'll stay in touch. And I hope people are getting all kinds of ideas about all the things that they want to date in the near future using the newest available technology to us. Like some of those things has just been around for 3 years. So yes.
Yeah, no, thanks to all.
Thank you, Aratz, for telling us all about.
For the invitation. And yeah, have a nice weekend.
Yes, you too. Laster arte. Venga.
Agur.
Agur.